It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good morning, everybody. Welcome to Tibbet's Physics. What is crappinin'? Today we're going to talk about induced EMF, or the induced electromotive force. Basically what we're going to talk about is how to create electricity without the use of a battery. And it turns out two people came up with this idea at the same time. One person was John Henry. He was an American science teacher. And the other person at the same time was Michael Faraday. And he was an English scientist. Both of these guys in 1831 came up with the same idea, and they said that a moving magnet down a coil of wire will induce a current and we could even say or potential difference, aka electricity. If we think about it, we know that a moving current will induce a magnetic field around that wire. So why not the opposite? If we move a magnet around the wire, can it push those charges to generate electricity? Now, common sense says that the American science teacher would get full credit for discovering this idea. But Michael Faraday, the English scientist, who apparently is a bit more reputable, receives credit for this concept. So what we're going to learn is what's called Faraday's law. Or if you want, maybe you could call it Henry's law. With Faraday's law, we're going to look at ways to increase the induced EMF. So the first way we could do it is we can just increase the speed of a magnet that's moving in and out of a coil of wire. So increase the speed of the magnet. The other method we could do is increase the number of coils. So if we have a 1 coil wire versus a 100 coil of wire, the 100 coil wire will have a greater induced EMF. So increase the number of coils. And then the last one is we could increase the strength of the magnet. So if we have a weak magnet versus a strong magnet, the stronger magnet will increase the induced EMF. So increase the strength of magnets. In order to determine the magnetic field strength that's inducing an EMF, we're going to calculate what's called the magnetic flux, which is similar to the electric flux. The symbol for magnetic flux is the Greek letter phi, P-H-I, and we'll put a subscript B for magnetic flux. And all it is the magnetic field strength within a coil of wire we say which induces the EMF. We can calculate the magnetic flux, or phi b, which is equal to the magnetic field strength times the cross-sectional area of the wire times the cosine of theta. Now, magnetic field strength and cross-sectional area we've defined before. What we need to do is define what the angle represents. In this case, it's slightly different than what we're used to. The angle is the angle between the magnetic field which is B, and the normal, which is perpendicular to the plane of the coil. So why don't we do a few examples and drawings to get an idea of what we mean in terms of what theta represents. The units for magnetic flux are called Webers, named after the Weber grill, or just capital W, lowercase b. Let's look at a couple of examples to get a better idea of how to look at the angle between the magnetic field and the normal of the plane of the wire. So why don't we draw a coil of wire first, which is represented with solid lines. We're going to take a slice of that wire, and we're going to shoot a magnet inside that coil of wire. So our magnetic field is going to the right of the page. What we want to look at is the normal to the plane of the wire. So if we're looking at the face of our slice, the normal is also going outwards, we'll label it normal, to the right of the page. And as we could see, the angle between the magnetic field and the normal is 0 degrees. And when we take the cosine of 0 degrees, we get 1. So our magnetic flux is max when the angle between the normal and the magnetic field is 0 degrees. Why don't we do the same thing, but now we'll rotate our wire 90 degrees. We'll look at a slice of that. And the magnetic field is still going to the right of the page. We want to look at the normal to the face of our slice of the wire. That's perpendicular. Shout out to Sean from Reserve Investments. And notice now the normal is perpendicular to the magnetic field. So our angle theta is 90 degrees. The cosine of 90 is 0, so our magnetic flux will be a min. So the magnetic flux will be a min when the normal to the coil of wire and the magnetic field are perpendicular to each other. Let's do an example. Practice problem number 4 from our worksheet. A conducting circular loop of radius 0.250 meters is placed in the xy plane in a uniform magnetic field of 0.360 teslas that points in the positive z direction as the normal to the plane. Letter A, calculate the magnetic flux through the loop. So we want to calculate phi b. So let's look at our formula for magnetic flux. Phi sub b is BA cosine of theta. In this case, theta is 0 because the magnetic field in the perpendicular to the plane of the coil of wire is 0 degrees, and we're told that they're in the same direction. So phi b is equal to b. We had to calculate the cross-sectional area, which is pi r squared, times the cosine of theta. And now we just plug and chug. So 0.360 teslas times pi times 0.250 meters squared, and the cosine of 0 degrees. Plug in our calculators and we get a magnetic flux of 0.0706 Webers. Okay, let's look at letter B. Suppose the loop is rotated clockwise around the x-axis, so the normal now points at a 45-degree angle with respect to the z-axis. Recalculate the magnetic flux through the loop. So in this case, the only thing that changes is now the angle between the plane, the normal to the plane of the coil, and the magnetic field is 45 degrees. So phi b will be the magnetic field strength times pi r squared times the only change is cosine of 45 degrees. When we plug that in our calculators, we get 0.0499 Webers. And that makes sense. As we get closer to 0 degrees, it should decrease. In this case, we do get a smaller magnetic flux. And the last question, what is a change in flux due to the rotation of the loop? So the change in phi b is just the final minus initial, or our answer from letter B minus our answer from letter A. So 0.0499 Webers minus 0.0706. And we get a change to be negative 0.0207 Webers. That's it for this video. If you found this useful, please like and subscribe. See ya!